Hello, everyone, and welcome back to Scientific and Medical Writing. This is week 10, part 2 in our video series, and we're going to start our first part here, talking about tables and figures, the juicy part, as I say, of our scientific publication. And usually tables and figures, they tell the story of your paper. So tables and figures will basically show the most important part or the main part of your paper. Usually when you submit this for publication or when you give it to a reviewer or an editor, they might only look at the results themselves since they might be they might be trained in interpreting the data, and they just take a look at the graphs and come up with their own sort of general take-home messages. After that, they might look at the abstracts, but generally the tables, figures, and abstracts are going to be looked at first. Your figures and tables should be able to stand alone without any writing. So even though we add results, a written part, up into our scientific publication, your tables should be simple enough and clear enough, tables and figures, so that when someone looks at them, they can get understanding of the work. People shouldn't have to look back at the tables or look back at the figures in order to determine what they're about. The figure should stand alone. And as I mentioned several times already now, tables and figures, that is really the main part of your publication. So they tell the full story. So you might have one or two or three, you might have four or five or six, but tables and figures can vary depending on how deep and how complex your story is. So John Claerbout of Stanford says, where a lot of this information comes from, is an article about computational science in a scientific publication isn't the scholarship itself. So the topic really isn't important. It's merely advertising the scholarship. The actual scholarship is the complete software development environment and the complete set of instructions which generated the figures. So if you just have one graph, basically, and the graph doesn't explain everything from your study, then your study is incomplete. So tables and figures, there should be enough to tell a complete story of the scientific research that you're doing. However, you don't want to overflood your paper by having a lot of tables and figures, so it's best to just have as few as possible. And remember, you don't need to have two tables or figures for the same data, right? Once you show the data once, you don't need to show it again a different way. As you become more experienced with statistics, you realize that you can use thousands of different ways to display the same piece of data. What we're going to learn in this class is what are some of the best ways we can use to display the data and how you can use that to display your story in the best way possible, which is usually the clearest way. So figures are different from tables. You know, a figure might be a photo, it might be an image, it could perhaps be like a graph, or something like that. A table is columns and rows, okay? But figures have a really strong visual impact, as you know, right? You see a photo, and we're going to take a look later on at one of the most influential papers of the 21st century called Deep Learning, where they talk about how you learn based off looking at images as one part of their study. So figures should tell a quick story. They should they should be clear. They should tell a quick, complete story, right? So figures should be able to stand alone, and they highlight a particular result. So you might have many aspects of your study. One figure might highlight one aspect of their study, as we did see in our resveratrol publication, where they had, if you took a look at that, you saw many different sorts of figures, images, histology-based images, and so on and so forth, blots, etc. Tables are different because they give more precise values. When you want to look at specific numbers, you provide a table, or when you want to look at specific variables. So figures generally are kind of like the paint brushes, the strokes moving, where tables are, very specific dots, if you will. And of course, every table and every figure needs some sort of title, so make sure your title displays the results accurately, and you use the same key terms in the title that you might use in the column or the text of the paper, right? And one of the basic things that you learn in high school when you do laboratory work are basic things like this, making sure the units are placed on the graph or on the table, making sure that they're correct, and making sure that the heading and the terms used all match. You don't want to confuse the reader. Keep it brief is really important, okay? So you don't need to overload the reader with a lot of different information, and you need to provide descriptive characteristics of the data in which you have. So for some of you who've taken statistics before, you might have a notion of what SD means. It stands for standard deviation, and that's a plus and minus symbol. And then we have N, which would be the average people or samples, okay? In this case, descriptive characteristics of the two treatment groups, means over standard deviations or average percentage, okay? So when you get the average of something, or when you get the sample size, there's big N, there's little n, then you display that, and that's really common in a figure. SD, standard deviation as well, you might put that in your results section. Sometimes you might want to, if your data is complex, or you want to kind of give a labeling diagram, you might want to give footnotes, all right? And a lot of times when we do statistics, when we do statistical significance, we're going to put different symbols as well, because we need to determine what part of the data is significantly different or not, and what are we comparing it to, right? So we're going to talk a little bit about statistics right now. This isn't a statistics course. There's a lot to go over, but we're just going to take a look at one example right now, because you're going to need it for the quiz. And statistics, I think, should be one of the core focuses of mathematics that you learn in high school and middle school, not algebra, not calculus. I think it should be statistics, but that's just my personal opinion. So we have different labels that we can use here. Sorry. And then we have something that's called the p-value, and I'm going to explain a little bit, just an introductory part of what that means when it comes to your tables and your figures. So I posted several different articles in your class, but one that I posted here was titled "The Role of Vitamin D in the Prevention of Coronavirus Disease, 2019, Infection and Mortality." So great, we're talking about coronavirus, something that you guys have here all the time. So we're not going to go too much into this right now, but I'm just going to give you some examples of what a table and a figure would look like. So this would be a table here, okay? And here we have countries, vitamin D levels, and coronavirus cases. And then here we have some figures, okay? So we can see here on the y-axis we have it labeled, and the x-axis we have it labeled, and so on and so forth. And just a moment here. Yeah, here we go. So the results in this paper, it's a short section. We have things like p-values and STDEV, standard deviation is another way. The p-value is what we call the significance value. So the p-value has nothing to do with the hypothesis, really. It doesn't confirm or reject the hypothesis or the question that we're asking in our study. It's just able to tell you, is the data different from one another, right? So this is actually not a good example of that, but we have tables and figures here. There's another one, paper that I posted here about coronavirus, hydrochloroquine and azithromycin as a treatment of COVID-19, results of an open-label, non-randomized trial. This is one of the most highly cited papers of the past year, the last year. It has thousands and thousands of citations on it, which is incredibly rare. Obviously, we have coronavirus, so there we go. And we can see it's structured a little differently, but it's similar to the vitamin D example. We have the abstract here, a short little preview. And I just want to show you a little bit of what I mean by the tables and figures and significance values here. So here we have our table, and we have our plus and minus side. We know that means standard deviation, as we mentioned before. And the big N here would be the number of patients. So 20, 16, and 36. And then we have the T and the p-value. So basically, let's say you had two groups, right? And this is different from this specific example. If you have two groups, one group or people who don't have coronavirus and one who have coronavirus, and then you want to test something, you would do something called a t-test, where a statistical analysis of a t-test where you're determining are they different? The coronavirus group and the non-coronavirus group. Is it different? Whatever you're measuring. Maybe you're measuring deaths or coughs or whatever. A t-value would say it's different. Now, you need to determine what your standard of different is, right? Do you want to say that difference is 50%? Well, that would be really bad. Do you want to say that the standard would be 60% of the time it's different? That would also be quite low. The standard in science is usually 5% same. Okay, so we use a p-value when we call this our significance value, p-value, statistical significance value. 0.05 is usually the standard. So that means if you have two groups, one is coronavirus, one has coronavirus, one doesn't, and you have a p-value of 0.05, not 0.05, then that means that if you compare the two groups and you run the t-test, the statistical analysis, and it gives you a number that's below 0.05, that means that more than 95% of the time the data is different. So you can say with a strong amount of significance, strong amount of certainty, that those two groups are different. And that's important to know if the groups are different or not. If the p-value would be higher than 0.05, that would mean that it's less than 95% different, which means they're more similar, all right? So it's a little bit of a difficult idea to compute in your mind, but I just want to let you know the p-value, the lower it is, the better it is. The higher it is, the worse it is. And you just have to take a look at the decimal places here. And so when you see something like a p-value, know its significance. ANOVA is a little different. That's when you have more than two variables. So a t-test would be 2. And then let's say you have one group that's coronavirus, and then coronavirus with the treatment, and then another group, no coronavirus, and then you have coronavirus with the treatment. That would be 4 different groups. You would need to do a more complex statistical analysis. And then you need to determine, well, which one of the 4 groups is different. Then you'd have to use some of our special symbols here. For tables, we're going to go over some examples, but really you just want to make your table readable. You want to make sure you follow the journal guidelines because everyone's different. Usually journal guidelines would be Roman or Arabic numbers, obviously, 1, 2, 3, 4, as we know. The table is centered. It's not to the left, it's not to the right. The columns and titles are centered as well. You have capital letters, everything's capitalized, and it's in italics, and then you might have some footnotes. Most journals also ask for you to add 3 horizontal lines, one above the column headings and one below the column headings and one below the data. And this is a good example of this here. We have one line here, one line there, and a third line there. This helps you follow the information. Oh, sorry, we'll come back to that one later. Okay, so let's continue here. So here's an example of a table, and I showed you one before, our 3 lines here. And here's another example of a better table where you have some gray areas here and there so that it's easier for you to read the specific row. In this example here that I provided you with here, they didn't do that, but that's because there's only 3 rows, so it's easy to compute and there's spaces in between. In the hydrochloroquine one, the table here, there's only 3, in this one there's only 4 columns. This one there's only 3, so we didn't need to use the gray bits, but this one, since there is, we might want to do that. You don't want to have a grid with your table, it just looks too cluttered. And you don't want to have no lines at all because sometimes it looks separated. Or you want to make sure that the lines are, the columns are centered, or they're at least in the all together in the same line. So you can see these are to the left, these are centered, doesn't look good. And then these are different as well. So you want to make sure you don't do that. And you don't need to have a ridiculous amount of decimal places. Usually we have 1, maybe 2, but it depends on what you're doing. Make sure that they're all similar at least. and make sure it's easy to read. In this case, this is 3, this is 2. These have none. So we need to make sure things match. And in this specific example, there are no units. So in maybe your high school biology class, you learned that when you submit your laboratory report and you didn't put units, maybe your teacher would take off a few points. So make sure that you have units. We need to know by age, is that in months, is that in years, is that in decades? BMI is, what are the units for that? So here's what not to do. In this case here, we have on an unnecessary column here because we have the overall, we have the bad witches, the good witches, and the p-value here. All right. So we probably wouldn't need to show all that information. We might need to just show the bad and the good witches and the p-value. So there are many different types of figures. As I mentioned before, when it comes to data, you want to have primary data. So we have what's called primary evidence figures. That might be an actual photo of something, a gel, a blot, as I mentioned before, an X-ray, if you're looking at, chest X-ray, for example. And remember, photos, people love photos. So primary evidence is really strong. A graph would be an example that is not primary evidence. You're taking the data and you are doing a statistical analysis and you are manipulating it in a specific way. Not necessarily in a negative way, hopefully not. And you can do that in many ways: bar graph, line graph, scatter plots. We're going to go over some examples. But you can also have diagrams or flowcharts. So especially in the methods section, if you are describing a specific sort of treatment or sort of methodology, which you might have developed as a medical doctor, a specific way to do a surgery or a specific way to treat a patient, you might want to give a diagram. And of course, you want to make sure your figures stand alone. And as I mentioned before, you want to give a little bit of a brief title. You want to make sure that the units are there, the p-values are there, and you give only the essential information. You don't want to give unnecessary information. And you can go back and take a look at the examples that I gave before. So this is an example of a legend. A legend basically explains all the information of your figure. We're going to take a look at examples like this later on when we take a look at more publications, but I'm just going to show you right now. In this specific case, we have our title over here, and we have our results over here. And there is no legend in this specific one. I think there might have been one here. Sorry. Yeah, okay. So a little bit of a legend here. They give a little bit of information on the data. This would be this last line over here. So a legend just kind of gives us additional information so that we can understand what we see. Here's an example of a primary evidence slide. We have a fluorescent microscopy scan or slice here. Really nice, really awesome, especially for good publications. Another example would be a blot where you measure the expression of a protein or DNA. Graphs, the second part, obviously you can have many different types of graphs, but we're going to talk a little bit about why you should use certain types of graphs and why you should not use certain others. Depends on what you want to do. So graphs are different from primary evidence figures, where primary evidence figures are you're going to be able to see it and understand just by looking at it and labeling the graph. But graphs are usually going to show a trend over time. So the third example that I'm going to give you here, where did it go here? Not the depot one. I think it is here we go, hydroxychloroquine one. You can see in this case, this is showing what did I mention here? Yeah, trends over time, where you have patients who are receiving treatment for coronavirus, and that's day 1, day 2, day 3, day 4, day 5, day 6. So this would be an example of a graph. Okay, so example of a line graph, I'm going to show you in a moment. We have bar graphs. So here's an example of a line graph here, as I mentioned before. So what this study did, I thought was really interesting, and one of the reasons why it's so fascinating is because not obviously it just dealt with coronavirus, but it also dealt with the trend of this treatment. So they treated patients with hydrochloroquine treatment only, or hydrochloroquine and azithromycin, and combined treatment here. And then they measured the percentage of patients with the PCR positive samples. So basically showing that they actually had coronavirus still at that time, or they were PCR positive, excuse me, at that time. And not only did they measure this over time, but they changed the p-value as well. So you can see here it starts at 0.55, then it goes to 0.25. By the time it gets to the end, it's 0.001. So that means not only is the trend going down, that means less PCR positive tests, but it's exponential in its growth because it becomes more and more different. So it works better and better over time, I guess you can say. So here that would be about 95% different. Here would be about 97% different. And then this would be like 99.55 different. And then by the time you get to down here, it's like 99.999, 99.99 different, right? So that means like it's really, really significantly different. And clear labels here and things like that. Graphs, as you can see, a little different here. Here's an example of two different control groups in a treatment. So you might have standard deviation lines here. And here the small n would be our sample size as well. So we have our standard deviation lines. And one thing to see about graphs, a little bit of statistical knowledge, you can see this is the lower end of the standard deviation, and you can see it's nowhere coming into contact with the other bar graph here. So we could probably assume just by looking at this, it probably is, these two groups are probably statistically significant from one another. So line graphs show information over time, as we saw in our example. Bar graphs are comparing two groups to the same point. So in this case, you can see here, you might be looking at some part in the middle, and this is higher, this is lower, for example. Scatter plots, they show the relationships between two different variables, and I think I'm going to stop this video here, and we're going to talk a little bit more about that in our next video. Give you guys a break. All right, we're going to continue the scientific manuscript as time goes on, and I'll see you in week 10, part 3. Have a good day. Bye-bye.